Welcome to Physical Science B, Week 3. We're now moving from Newton's laws of motion to his law of universal gravitation. We're going to talk about how those two things relate today. So for many years it was thought that space travel beyond Earth's atmosphere would be impossible because in space there would be nothing to push off of. In other words, the idea is that when you are accelerating, maybe using a jet engine or something, you need to be pushing off the ground, like a rocket, like shooting its fuel onto the ground, right? To create the pressure to sort of push the rocket up. Or you need to be pushing that rocket fuel or something else out the back end against the air in the atmosphere that can then cause that to go forward. But in recent centuries, we've realized that that's not the case. We don't need air or land to push off of with our jet engines in order to get us moving in the opposite direction. So why did we discover that space travel was possible, and why have we now proved that it is possible? What's wrong about that way of thinking of it? I'd like you to answer that for your first lecture question. If you have trouble answering it, no problem. Just do the best you can to think about what the real situation is, why we don't need to push off of the air or the land in order to get ourselves moving. You can pause the video to answer that question and start up again now. Our keywords for today are mass, jet propulsion, gravity, and exponent. And the answer, as I preemptively put down there, is Newton's third law. That's the reason we were wrong, because you don't need something to push off of, though Newton's third law does say for every action there's an equal and opposite reaction. But the reason why it works is because you've already pushed off when you push those, or when the jet fuel burned and that those water molecules or whatever the combustion products were shot out the end of that jet engine. Well, that shot you in the other direction, just like the spaceman we maybe talked about last week. When you're floating in space and you throw a rock in one direction, that's going to cause you to move in the other direction. Not if there doesn't have to be any air out there for that to function, for that to work. So this rocket engine here is shooting air so fast, each little tiny water molecule being shot down so fast that it's causing a thrust in the other direction, an equal and opposite reaction. So again, we're moving from Newton's laws to gravitation, acceleration, and again our keywords: mass, jet propulsion, gravity, and exponents. We're going to talk a little bit about exponents. Why are we doing this? Well, of course, the state standards, and because it's good to learn, right? We're going to apply the laws of motion and gravitation to describe the interaction of forces acting on an object and the resultant motion. So we're moving again, like I said, from Newton's laws of motion to his law of universal gravitation. He did a lot, right? I mean, how could you come up with all that yourself? But he did. He quantified it. He was a genius. He was also kind of crazy and a little bit egotistical, but definitely a genius of the first order. So reviewing his laws of motion, we remember inertia. Objects in motion tend to stay in motion. So we don't always realize that when we're seeing like an asteroid or something floating around near Earth. But they're actually moving quite quickly through space, and there's nothing to slow them down until they enter our atmosphere, and that's when they become meteors. And they slow down, burn up, usually explode, actually, if they're big enough. And the fragments are scattered through Earth. Newton's second law, of course, relates acceleration to force and mass. So F equals ma. Force is equal to a mass times an acceleration. So if you are applying a force to something, you're able to give a certain mass, a certain amount of acceleration, depending on how much force you're applying. So it's proportional to force. The more force, the more acceleration. And it's inversely proportional to mass, which means the more mass, the less acceleration. The bigger you are, the harder it is for a force to propel you. And you can, of course, remember Star Wars. Luke, use the mass times acceleration. Or perhaps if you were Yoda, you could say, Luke, mass times acceleration, use, or whatever. Sorry, I apologize for that. So the bigger the mass, the smaller the acceleration. All the stuff I just said. And the third law, that forces never act alone. Same reason that that space travel is possible. We can actually travel to the moon or to outside of our atmosphere, is because forces never act alone. You shoot that water molecule out the back end, it's going to have an effect on you. Just like this gun, the bullet doesn't need the air to sort of push off of to kind of give force to the gun. As soon as the bullet begins to move through the gun's barrel, the gun is going to move in the opposite direction, which is why you need to brace it, of course, against your shoulder, not against your face or your eye. Just a fair warning there. Have you seen the movie Gravity? Maybe not. It was came out a few years ago. I don't know if most people saw it. Sandra Bullock and George Clooney. The big joke, I think, being a movie where George Clooney would rather float off into space and die than spend one more minute with a woman his own age. Which is funny because he usually dates women that are much younger than him. So, is this a good representation of no gravity? The idea of them, so they were in space, they were working on a satellite. Here's the International Space Station, for example. So, is this guy sort of floating in space here, as he's orbiting, or just left, I guess, he's sort of floating away from this space station? Is he or she, maybe that's Sandra Bullock, I don't know which character that is that a good representation of there being no gravity, of what it means for there to be no gravity? That's your second lecture question. Go ahead and answer that. And we'll get started. So, of course, on the space station, you may have seen videos that can float around like this, right? So you'd think, well, of course there's no gravity. Or if they brought, say, a fidget spinner to space, which apparently we spent your tax dollars doing, is that fidget spinner experiencing no gravity? Well, the fact of the matter is it's experiencing weightlessness, but that's not because there's no gravity. Actually, when you are 250 miles above Earth, like the International Space Station is, you're still feeling 90% of Earth's pull on you. But the reason why weightlessness is experienced is because you're in free fall. You're free falling with the satellite towards Earth. Well, then you might ask yourself, well, how come I never hit the Earth? Well, that's the question, and that's actually what Newton realized when he developed his law of universal gravitation, is that you can be in free fall and never hit what you're falling towards, kind of. But only on one condition that we'll see in just a second. So this is Newton's kind of other law. We have his laws of motion already, but he also developed this law of universal gravitation when he saw an apple falling from a tree. Now, of course, the reason why that's important is not because he realized, oh, hey, apples fall down, so there's gravity. Like, everybody knew that. But he thought to himself, you know what? For centuries, we've thought that the heavens obey different laws, totally different laws than here on Earth. But what if they actually obey the same law? What if gravity is acting out there in the same way that it acts here? So there's something, in a sense, universal. That's why he called it universal gravitation. It applies everywhere. And the heavens obey the same laws as Earth. And we realized shortly before Newton that the Earth was, first of all, a sphere, kind of like the moon seems to be. Galileo had realized that the moon itself had some features on it. It wasn't just sort of this blank orb of light, but it was actually, it actually had some relief. And because of that, maybe it's just sort of a normal rocky surface, just like Earth or something like that. And what Newton realized was that maybe the moon is actually falling towards Earth like a satellite and just never hits it. So you could imagine if you had a cannon firing cannonballs, and it fired one, cannonball A, fell here, but it said, well, that's not far enough, I have to fire farther, so it fired cannonball B a little farther, it landed over here. Well, you can imagine that if you have inertia going in that direction, and you're increasing inertia, then even if the force of gravity is always acting towards the center, if you have enough inertia moving you in a sideways direction, then perhaps you could fire a cannonball that would never land. Because as much as the inertia was carrying it there, gravity was acting on it in a downward direction to keep it close to the Earth, but never able to act on it quickly enough to cause it to actually fall to the Earth, and that's exactly how satellites work. That's how orbit works. That's how the moon works. That's why even the moon experiences Earth's gravity. It's not like there's necessarily no gravity on the moon or no attraction. If you were standing on the moon, you'd still have attraction for the Earth. Not as much as for the moon, because you're right next to the moon. But you'd still have attraction for the Earth, and you and the moon would be orbiting around it, falling towards it, but moving so quickly that you're able to maintain that orbit. So that's all that orbitational, that's all that orbit is a continuous motion around the Earth. You're in free fall constantly. You never actually hit what you're going for. You could imagine kind of like, if I were to put a pen here, you know, if at this point in its flight, gravity is acting to pull it down there, but you can imagine its inertia is carrying it so fast, still even here, that it's not able to fall. Inertia would try to carry it out here, you know, but its actual resultant motion, the gravity's pulling it a little bit, so it pulls it down here some, and now the gravity's acting in this direction. So it doesn't quite achieve that full resultant straight motion that you'd expect from a body, but it maintains this constant orbit around the Earth. So now at this point, the satellite or the cannonball or whatever wants to go that direction, but gravity's pulling it down a little bit, so it still moves here. Now, of course, with a cannonball, you've got air resistance to slow that cannonball down. But with things beyond our atmosphere in outer space, there's nothing to slow it down, and so it can stay in orbit forever, virtually forever. All right, so now what we're going to do is learn about his law, because he didn't just develop the idea that they obey the same laws, but he sort of calculated them. And it was much easier to do when you could use bodies that you could guess their size, like bodies going around the sun or the moon or whatever else, and kind of figure out, well, if you have two bodies of different masses, m1 and m2, and they're separated by a distance r, then there should be an expected force related to those. And then this gravitational constant helps us to relate the units of kilograms and distance to the units of force. And that constant is this number right here. So this is the equation that tells us, if you have two masses of this size and this distance apart, how much force they should be feeling for each other. As we do, we call that force weight when we're the ones standing on Earth. It's how much we weigh. That's the force we're feeling from Earth's gravity, because Earth is mass 1, and we, in that case, would be mass 2, tiny little person. But you multiply those together and divide them by the distance we are from the average center of the Earth, and square that, you're going to be getting then a force. This gravitational constant, I would just point out, has an exponent. That's one of our words for the day, you recall. And you're going to be learning about scientific notation soon. Exponents, first of all, mathematically, they simply tell you how many times to multiply something times itself. So in this case, you multiply 10 times itself negative 11 times. Now the weird thing about that is when you have a negative exponent, what you're actually doing is doing 1 over the exponent. So it's 1 over 10 to the 11th power. So 1 over 10 times itself 11 times is 10 to the negative 11. And so actually that makes this a very small number, because you're multiplying 6.7 times 1 divided by 10 to the 11th power. And that gives you a very small number. In fact, here's that small number right here. 0.000067. So that is an exponent. You'll be using those a lot to actually make calculations easier soon. So before we actually do a couple calculations with this gravitational formula, I want you to first answer for your next lecture question, what are two things that influence gravitational force? And you can see them both right here. Two things that are going to change how much force these two objects feel for each other. What is it about them or their relationship that's going to cause them to feel more or less force? What are those two things that will influence gravitational force? Again, I'm not looking for right answers. I'm just looking for careful thinking, and hopefully it's helping you to stay on track and pay attention. Well, the two things, of course, are the masses of the objects and the distance between them. So those are the two things that are going to determine how much force this object feels. All right, so here's an example. If we ignore the Earth's gravity and just think of these two objects that are attracted to each other, recall that gravity doesn't just exist between large planets and other things. It exists between everything. which means my two fingers have gravitational attraction for each other right now. They feel each other somehow gravitationally, which is really wild to think about. And my finger even feels the sun gravitationally and far distant stars gravitationally. They're somehow in contact gravitationally, and they feel each other's pulling ever so slightly in this case on each other, but they do feel it. It's one of the mysteries of the universe. We kind of know how it works, or we can quantify it, but we really have no idea why there would be objects attracting each other like that and why it would work over such vast distances. But it does. So if we imagine these two masses, these large balls, one is 100 kilograms and one is 50 kilograms, and we have them separated by 4 meters, 2, 3, 4, 5, 6, so 6 minus 2 is 4 meters. Their centers are separated by 4 meters. Then, using Newton's formula, we're going to get a gravitational attraction of 20, or 0.00000020,960. These are the numbers you need to pay attention here at the end. So now we're going to use that equation to see what would happen if we change things a little bit. So what would happen to the force if you doubled the weight of mass 2? So if mass 2 is no longer 50 kilograms, but 100 kilograms, what would happen to the force between these two objects? And you can see that the force is equal on both of them, right? Because of Newton's third law. Same law we talked about at the beginning of class with jet propulsion, but Newton's third law applies here as well. If this exerts a force on this object exerts a force on this object. Gravitation just is more of a pull than a push, like we've been talking about so far. So if we double this force, or double this mass, what's going to happen to the force? So you can go ahead and answer that, and try to be as specific as you can with your answer for your next lecture question. I think that's number 3. Okay, well, if you answer that the force is going to go up, you'll be right? Of course, the force is going to go up because these two things are connected. But specifically, the force is actually going to double. That's because of the relationship here. You can imagine that if you were to double mass 2 in this case, whatever that number is, who cares? We just multiply it times 2. Well, if you multiply one side of an equation times 2, or even one part of it, because that's going to end up multiplying the whole thing times 2, well, that means you have to multiply the other side times 2. So it's going to double the force. So we go from 0020 to 0041921. It's rounded off there a little bit, but that is double the force when we up this to 100 kilograms. All right, now let's think about what happens when we double the distance between the centers of mass. So instead of being 4 meters apart, from 2 to 6, we're going to move this ball back to the position of 10, and their centers will then be 8 meters apart, twice as far apart. How much force are they going to feel in that case? So you can answer that for your next lecture question. I guess that's number 4. What will happen to the force these two objects are feeling, the gravitational force, or the force due to gravity that they feel, if their position relative to each other is doubled? All right, so you probably answered, or hopefully you answered, that if you pull this back, it's going to go down. And that makes sense, right? Because if distance is on the bottom here, and if you make that number bigger, the number on the bottom, that's going to decrease the overall, write that down actually, I guess. If you make the number on the bottom bigger, twice as big, that's going to decrease this overall term because you're increasing a denominator, something on the bottom of it, making the fraction smaller, basically, because the bottom part is bigger. That's going to decrease then this. But by how much? Some of you might have said that you're going to have half the force because you're twice the distance. And that would seem to make sense, logically. But that's not how it works. It actually works as a square of the distance. Which means that if you double the distance, let's say from 4, if r equals 4, then r squared is going to equal 4 squared, which is what? 16. Hopefully you know your times tables. 4 times 4 is 16. And if we double that r to make it 8 meters, and we square that, 8 squared, or 8 times 8, is what? Do you remember? 64. And 64 is 4 times what 16 is, which means that what you're actually doing is reducing the force by a factor of 4. So in other words, I'll just put divided by, kind of hard to do, divided by 4. Which means that instead of having it, you're going to divide it by 4. And that tends to be how the these powers work, or square, in the denominator. So we double the distance, and we'll see now that we go from 2096 to 5. So basically, instead of we go from 20 to 5 when we're looking at this decimal point situation. So 0000 it was 20, and now it's 05 for these digits here. So we've reduced it by a factor of 4. So that's important to remember, that when you distance has a disproportionate or a more radical effect than the mass itself, which is why moving merely 250 miles from the surface of Earth actually reduces your mass by 90% of its normal mass. That's pretty significant for not really moving all that far. In fact, even if you climb to the top of a mountain, like Mount Everest or something, your weight will decrease by, I think, nearly 1% or something like that of what it normally would be. So it's something substantial. All right, so your gravitational force, and this is the last thing I want to leave you with. For us on Earth, it's just our weight. And so we, as people, measure our weight, and what we're measuring is the force due to gravitational attraction to the Earth. And you need to remember that the Earth actually feels a gravitational attraction towards us in the same way. Of course, it's much smaller, and the Earth being much bigger doesn't notice. But, the bigger you get, the bigger the more the Earth weighs, to you. So in other words, when you put on weight, you feel heavier. But the Earth also feels your weight more, or feels more attraction towards you. So in a sense, it feels heavier as well. All right, that's gravitational attraction. I will see you guys next time.